So today we're going to be going over how to derive Binet's formula. And Binet's formula lets you jump directly to the nth Fibonacci number without computing all the previous ones. So the first thing we're going to do is to have the definition of the Fibonacci sequence, which has the initial conditions of f not equaling 0 and f1 equaling 1, with our formula being fn is equal to fn minus 1 plus fn minus 2, with our goal here to find a closed formula for f of n. So the way that we're going to do this is guess that the sequence might have solutions of the form fn is equal to r to the n, where r is a constant. Now, we're able to use a standard trick from exponential sequences as they behave nicely under shifts, so that we're able to plug this into the recurrence. So we get r to the n is equal to r to the n minus 1 plus r to the n minus 2. And we want to now divide both sides by r to the n minus 2. Now this will leave us with the formula of r squared is equaling to r plus 1. And this is known as the characteristic equation of the recurrence. Now, as you notice, this can be changed into a quadratic, because this will give us r squared minus r minus 1 equaling to 0. And now with the quadratic formula, we find that r is equal to 1 plus or minus the square root of 5, all divided by 2. And now this gives us two extremely famous roots. The first one being phi, which is the golden ratio of 1 plus root 5 over 2, and it'll give us psi, which is the opposite. It's the 1 minus root 5 over 2. It's the conjugate of the golden formula. Now, since the recurrence is linear and has two distinct roots, the general solution is going to be fn is equal to a phi of n plus b psi of n. So the recurrence is linear and has two distinct roots. So this gives us the general solution, again, of fn is equal to a phi of n plus b psi of n. And here a and b are constants. But they are determined by the initial conditions. So now we want to solve for a and b. So we're going to start off with our first initial condition of the Fibonacci, which was our n equaling to 0. So this gives us f naught is equal to 0, which, plugging into our formula, gives us just a plus b. Since phi to the 0 is equal to 1, and psi to the 0 is equal to 1. So now this gives us that b is equal to negative a, or vice versa. Next up, we want to use our second initial condition that we had, which was our n equaling to 1. So our f1 is equal to 1, which is equal to a, and this is going to be phi to the 1, which is just phi, plus b times psi to the 1, which again is just psi. And now we're going to substitute our b equaling to negative a. So this gives us 1 is equal to a, and then this will be phi minus psi now, which gives us the formula of a being equal to 1 over phi minus psi. But we're not done because we still need to compute what the denominator is equal to. But that's kind of simple because we know what both of them already are. So here we're going to get phi minus psi is equal to our 1 plus root 5 over 2 minus 1 minus root 5 over 2, which if you simplify will just give you root 5. So now, putting this back into our formula, we get that a is equal to 1 over root 5, and b is just the negative version of a. So this is going to be negative 1 over root 5. Now substituting these values back into our general solution, we get that f of n is equal to 1 over root 5 times phi of n minus 1 over root 5 psi to the power of n. And now we can factor out the 1 over root 5. So f of n is equal to 1 over root 5 multiplied by phi to the n minus psi to the n. Which you can make look a little bit neater, or just a little more simple if you don't want to work in phi and psi, because this will be 1 over root 5 multiplied by 1 plus root 5 over 2 to the power of n minus 1 minus root 5 over 2 to the power of n. And this expresses the Fibonacci numbers using only powers, subtraction, and division with no recursion at all. And that's the full derivation of Binet's formula. If you liked, let me know what else you want to see in the comments.